Section 23.2, Models of the Atom. The objectives here are going to be to discuss the different models of the atom, to recognize the different absorption spectrums for each element, and to explain atomic spectra using the Bohr's model of the atom. So first we can talk about old models, and this was during Newton's time. And old models of the atom were just simply thought of to be tiny spheres that were indestructible. And that was what the atom was thought of. There's no ideas of electrons, protons, anything else going on, just the atom itself. Then around 18, the next model came out, which was the Thompson model. And this model stated that the electrons were embedded in a spherical volume of positive charge. And that's what you're seeing here. Imagine this spherical object, the red, with these these blue electrons embedded all in the red sphere of mass. Now, this red object was considered to have a positive net charge, and then the negative charges of each electron meant that this was still considered to be a neutral charge. Now, the one thing here was that this came about as the result of the discovery of the electrical nature of the atom. When the atom was discovered to be able to conduct electricity or have some electrical nature, it meant that there had to be something with charges or some sort of polarity or electric charge on it. And you could think of this analogous to like a watermelon with seeds all in it, or a muffin, a chocolate chip muffin with chocolate chips all in the muffin. Now, the Rutherford model was in 1911, and this stated that the electrons orbit a positively charged central nucleus. And this is in a manner similar to planets orbiting the sun. So here's your central nucleus with positive charge, and these are the electrons thought to be orbiting or spinning around that positive nucleus. Now, this came about as a result of the gold foil experiment, which is also known as the Geiger-Marsden experiment. This was performed by Hans Geiger and Ernest Marsden, and it was under the direction of Rutherford. So again, under his direction. Now, what happened here was this. The gold foil experiment proved that the plum pudding model, that it was the traditional one, the previous one, the Thompson model, which we called like the watermelon model, it was incorrect because of the fact that alpha particles were shot at a gold foil. And what they noticed was that several of them were deflected or reflected. And what this meant was that there was a central positive charge that has a relatively large mass or charge to it, because alpha particles are really just helium nuclei. That's what an alpha particle really is. It's two protons and two neutrons. So when an alpha particle would hit the nucleus, it would rebound or would want to go away from it because two positives push each other apart. So what was happening is these alpha particles were getting fired, and a lot of them were passing through, like this. But every once in a while, one of them will get deflected by the nucleus. And what happened is that since many of the particles passed through the foil, the positive center charge had to be deducted to be relatively small compared to the rest of the atom, which really meant that the atom is made up of mostly empty space. That was the major conclusion of this. And something else that Rutherford is credited for, actually, is he's firstly credited for like splitting the atom in a nuclear reaction between nitrogen and alpha particles. And this is where he discovered and actually named the proton. Now, the next important discovery was the idea of atomic spectra. And atomic spectra are when a potential difference is applied across an atomic gas. So looking at this picture here, there's a gas in a gas tube, and there's a voltage applied across this. And as a result, a current is produced in the gas, and that tube gives off light. And you can see the light of different colors here. So what happens is when the light passes through this single slit, which then goes into the prism breaks up that light into its different colors of the spectrum. Now, the crazy discovery was that each element has a different atomic spectrum. So if the element that was in the atomic gas was hydrogen versus, in this case, mercury versus helium, a different color or a different set of spectra would show up as a result. And each atom or each atomic gas had a unique spectra. And this was mainly used in the big idea is that it can be helped to identify elements in a mixture. So if you have a mixture of elements and you could break it up, you could figure out what elements that mixture is made up of. And then finally, when a solar spectrum was discovered, the spectral lines didn't correspond to any known element, and that was here, helium. And as a result, this was considered a new element at the time. And since it was the solar spectrum, they called it helium after the word for sun in Greek, helios. Now in 1913, the Bohr model told us that electrons are found at stable orbits, but can jump from one to another at stable, specific orbits. Now, other things that the model told us were that the atom is held together by the positive nucleus and the negative electrons around it, and there's a force that's keeping them from attracting to one another, and it's not spiraling inward. The electrons are not spiraling toward the center of the atom and crashing into it. We also found out the electron radiates energy when it jumps from an outer level to an inner level, and not continuously. It doesn't always give off some sort of energy. And third, the frequency of that radiation emitted in the jump is related to the change in the atom's energy. And this came about from using Planck's relation, or Planck's equation we call it too, E equals h omega, where we have the energy equals Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds, times the frequency of the radiation that's emitted. And we're going to take a look at this in a moment on the next slide to explain how this really works a little bit more. But this is energy in joules, this is Planck's constant, and this is frequency in hertz. Next we'll talk about how energy levels jumps account for the discrete spectral lines that we saw earlier. And first we'll start by defining something called a photon, and a photon is one unit of light energy, a quantum of light energy. Now, spontaneous emission is when a light of continuous spectrum shines on an atom. An electron can jump to a higher energy level. So what that means is there's some incoming light or photon that hits the electron, causing the electron to jump out to an excited state. Now, what happens is this can only really happen if the energy of the photon itself matches the energy separation between these two levels. So say the amount of energy at this level is like a number like 5, forget units, and the energy level of this is 7. The difference between 5 and 7 is 2. So the photon has to have an energy level of 2. If the photon had an energy level of 2, hitting an electron here at energy level 5, if this were 7, it would jump. But if the photon had an energy level of 1, well, 5 plus 1 gives us 6. And if this ring has an energy of 7, 6 would be in here somewhere, and it cannot jump there. It has to go from one energy level to the next. Now, the next thing is that once it's in an excited state, it's going to jump back down to the lower level. It wants to come back down to a lower level, just like we always want to lower our potential energy. You always want to come out to a lower amount of energy or an equilibrium state. So when this electron jumps back down, it emits some sort of radiation. And these are responsible for those bright lines that you see in the emission spectrum. Now, an application or an idea of this is the Northern Lights, Aurora Borealis. And there, the photons from the sun get trapped in the Earth's magnetic field at the pole. So here's your Earth, right? And the magnetic field, as we remember, looks like this. Well, the photons get trapped in the magnetic field toward the pole, and what happens is they interact with the gaseous atoms that are there. And when they do that, if you know that the sky is made up of many gases, argon, boron, helium, hydrogen, so it interacts with those gases and you get the different myriad of colors. You get that little display of colors in the Northern Lights where you see many different colors from those atomic spectra that you would see. Let's look at an example here. Example 1 says an excited electron in a mercury atom, so it means it's already at a higher state, drops from energy level 4 to energy level 2. So we're saying it's on like the 4th ring to the 2nd ring. So here's our hydrogen, or our mercury atom. There's the nucleus. Ring 1, ring 2, ring 3, and ring 4. Well, the electron's here, and it's in an excited state, and it wants to be back in the 2nd state where it comes from, and it jumps back down to here. So that means that earlier, some sort of energy level of photon must have hit this, with the exact difference in amount of energy between these two to excite it up here, but now it's falling back. So we're told that the energy levels for 2 and 4 are given. This energy level is 5.43 electron volts, and this energy level is 4.66 electron volts. Now, what we'll do is convert electron volts to joules in a moment to then know what our difference, our delta E, is in this equation. So we're going to try and figure out the frequency of the radiation emitted. So let's use Planck's relation. We'll say again E equals h omega. Well, E is really the difference in energy levels. So E in this case is the difference. 5.43 minus 4.66. So let's go ahead and subtract these two now and get 0.77 electron volts. Now we have to convert this number to joules, and the reason we remember that is because Planck's constant, the units here are joules times second. The units of frequency are hertz, which is 1 over second. So this only works, and these only cancel, resulting in an energy level of, or energy units of joules. So this needs to be converted to joules. So we have 0.77 electron volts, and we'll multiply that times our conversion factor in this problem, which tells us that 1 electron volt is equivalent to 1.6 times 10 to the negative 19 joules. The same number, not the same units though, as the elementary charge of 1.6 times 10 to the negative 19 coulombs. Okay, so this is the same exact number you're going to use when you look at the elementary charge, as opposed to this number here with electron volts, which converts to joules and not coulombs. So multiplying here, we're going to see our electron volts cancel. We end up getting a value of 1.2 times 10 to the negative 19 joules of energy. Now we place that for energy, and again we're solving for frequency. So we will divide by h on both sides, giving us the amount of energy over h is equal to our frequency of the radiation emitted. Plugging in 1.2 times 10 to the negative 19 joules over 6.63 times 10 to the negative 34 joules seconds. Notice joules cancel, giving us units of some number times 1 over seconds, right? Seconds are in the denominator, and 1 over seconds is really hertz. So let's divide these two quantities next to get 1.8 times 10 to the 14. And let's write this, the correct units of hertz, as our final answer. Now along the electromagnetic spectrum, this would be infrared waves.